Okay, so we were here. Suppose we need to find a prime ideal Q such that A I think is not 0 in AQ. Which means that A times something W not in Q is 0. oh sorry, this thing is not 0 for all. For all W not in Q. I think I know now how to proceed with this. So you take the annihilator of A. Okay, so if you take the annihilator of A, so I think the proof of this thing is similar in spirit to the thing that we proved, that if that being 0 is a local property. Yeah, I think the proof is similar in spirit. So annihilator of A, which is the set of all B in A such that BA is equals to 0, which means like so what? So this is an ideal of A. This thing is an ideal of A because it is closed under addition, negation, negatives, multiplication, and stuff like that. But it is not the whole ideal. It is properly contained in A, because if 1 lies in this ideal, then that would mean that A is 0. But we know that A is non-zero from here. So this is a proper ideal. We can take a maximal ideal M containing AN, because we know that every proper ideal is contained in some maximal ideal. And now I claim that A over S, or A over 1 for that reason, is not 0 in AM, because if W does not belongs to M, then W does not belongs to AN and A, which means then AW is not 0. So A over 1 is not 0. And it's clearly nilpotent. Clearly A over 1 is nilpotent in AM as A over I don't even need to write that down why it's nilpotent. Because when you multiply it by itself n times, the numerator gets multiplied by itself n times, and it has to become 0. So it's clearly nilpotent. So the next part of the problem says that if AP is an integral, so we have just shown that if each if AP does not contain any nilpotent element, then A does not contain any nilpotent. So that's kind of a way we are gathering up local information to get a global information. So now we want to see that if each AP is an integral domain, is A necessarily an integral domain? Well, it's a question, so that means that it's probably not true. So we need to find some ring which is not an integral domain, but when you take its localization by P, it is. And I think the example, counterexample would not be easy. So we want AP to be integral domain, but not A. So the first part of the problem actually gives us some information about how we can construct a counterexample. We should not be taking a ring for which AP we should what did I mean to say? So if each AP is an integral domain, then we know, yeah. So the first part tells us this: if we want to construct a counterexample, then the counterexample must satisfy this. So if A is a counterexample, that AP, suppose AP is an integral domain. AP is an integral domain, but A is not. Then because AP does not contain any nilpotent elements, it means and A should also not contain nilpotent element. Does not contain nilpotent elements. So we have to construct an example of a ring which is not an integral domain and also does not contain any nilpotent elements. Is there an example of a ring that is not an integral domain but also does not contain any nilpotent elements? I think we should look for something like the n for some reason. I think if you take n to be a product of distinct primes, then the n does not have nilpotent elements. Because in order for an element to belong to the n, and en equals to 0, we must have that A contains all the factors of n, sorry. So in this case, if it contains all the factors of n which are distinct primes, then it must be a multiple of n, and so it should be 0. So the n does not contain nilpotent elements, and it's also not an integral domain, so we should probably take the simplest example, maybe Z6. So Z6 does not have any nilpotent elements, and you can also check this manually. 1, 2, 3, 0. I mean, when I say it does not have any nilpotent elements, I mean non-zero nilpotent elements. So clearly 1 is not nilpotent, clearly 2 is not nilpotent, because it will be power of 2, and 3 wouldn't be able to divide. And 3 is not a nilpotent, 4 is not nilpotent, 5 is not nilpotent. So this is not integral domain, but also does not contain any nilpotent elements. Let's see what are prime ideals in it. So prime ideals in ZP look like the PZ over Z 6Z such that the P divides 6, I guess, and so it's either 2Z or 6Z, or or 3Z or 6Z. Yeah, these are only prime ideals, I believe. And so we just have to check that Z6, we have to if A is Z6, then we have to check that A P1 and and AB two integral domains. So what is AP1? So these are all elements of the form A over some 2B this. And oh, sorry. For A belongs to Z6, AP belongs to Z6, and B does not belongs to Z6, Z2Z over 6Z, not belongs to 2Z over 6Z, which means that B is not even. And AP2 is A over B. AB again belongs to C6, and in this case 3 does not divide B. So we already know that these two are local rings, which means that they contain a unique maximal ideal. Oh, we have to just show that these are integral domains. I think this should not be difficult, because if we have A over B and we multiply it by A bar over B bar and C, we want to show that if this thing is 0, then one of them is 0, and this implies that A bar over A bar is 0, which means A bar times something C is equals to 0, where C bar does not belongs to 2Z or 6Z, which means that 2 does not divide C. So because this thing means C is equals to 0, and 2 does not divide C, it implies that 2 divides A per, because 2 divides this whole thing as so which in turn implies that 2 divides A, or 2 divides A this. Okay, so if 2 divides A, then A times 3 bar is equals to 0 and 3 belongs to 6, 2z over 6z. And if 2 this, then A bar times 3 bar is equals to 0, and again same. So this shows that our B bar is equals to 0, or A prime bar over B prime bar is equals to 0. Now for the other thing, suppose that we have A over B times A prime bar over B prime bar is equals to 0 in AP2, then A times C is equals to 0 for some C does not belong to P2, which means that 3 does not divide C. So this implies C equals to 0, which by 6 divides C. 3 divides C divides C. 3 divides A, or 3 divides this. So 3 divides A. If 3 divides A, then A bar times 2 bar is equal to 0, and 2 bar belongs to 3z over 2 bar. Sorry, this does not. 2 bar does not belongs to 3z over 6z. So this means that A bar over B bar is equals to 0. And if this thing, then same. So thus we have shown that the 6 is not an integral domain. But AP is an integral domain for every P, for every prime P. And I think we could have taken any Zn where n is a distinct, n is a product of distinct primes. I think this should also work, because I think the same work. So thank you for sticking by, and we are going to finish it.